Hello dear students, welcome to mathematics class. In this class, let us discuss the example on Riemann integrable, that is in the second unit. So here the example is, if f of x is defined in the closed interval 0 1 as f of x equal to minus 1 whole power r minus 1 for 1 by r plus 1 less than x less than 1 by r, where r takes the values from 1 to n, then show that f of x is r integrable in the closed interval 0 1 and also integration over 0 to 1 f of x dx is equal to log 4 minus 1. So here f of x, so here it is the definition of the function, that f of x equal to minus 1 whole power r minus 1 for here. So this is the domain for the function f of x. Domain means the values of x from where we need to substitute in the function. So here the values of x lies between 1 by r plus 1 and 1 by r, and the values of r varies from 1 to n. So it is given, and we need to prove that f of x is Riemann integrable in the closed interval 0 1, and also the value of that r integral, that Riemann integral is equal to log 4 minus 1. Now let us solve this one. So here given that f of x equal to minus 1 whole power r minus 1 for the values of x lies between 1 by r plus 1 and 1 by r. Now go on substituting the values of r. So here for r equal to 1, f of x is equal to 1, because here f of x equal to minus 1 whole power r minus 1, and if you substitute r is equal to 1, this becomes minus 1 whole power 0, that is equal to 1, that is for 1 by 2 less than x less than 1. So here this is 1, because r is equal to 1, so 1 by 1 plus 1, that is 1 by 2 less than x less than 1 by 1, that is 1, and for r equal to 2, here minus 1 whole power 2 minus 1, that is minus 1 whole power 1, that is equal to minus 1, for 1 by 3 less than x less than 1 by 2, by substituting r equal to 2 in this equation. Then for r equal to 3, this becomes minus 1 whole power 3 minus 1, that is minus 1 whole square, that is plus 1. So therefore f of x becomes positive 1 for 1 by 4 less than x less than 1 by 3, and so on. Here we can write for r is equal to n, it becomes f of x equal to minus 1 whole power n minus 1 for 1 divided by n plus 1 less than x less than 1 by n. So according to the definition of the function f of x. Now here we can check the value of f of x. So either it is equal to plus 1 or minus 1, is it right? So therefore the value of x lies between minus 1 and plus 1 for all x belongs to the closed interval 0 1. So therefore here whatever may be the value of x in the interval 0 to 1, the value of x varies in between minus 1 and plus 1. So therefore it implies that f of x is bounded. And also here we can see that f of x is not defined. F of x is not defined at the points 1 by 2, 1 by 3, 1 by 4 and so on, because here x is not exactly equal to 1 by 2. Whenever x is less than 1 by 2, the function is equal to 1, and whenever x is less than 1 by 3, less than 1 by 4, less than 1 by 5, less than 1 by 6 and so on. So therefore whenever x equal to 1 by 2, 1 by 3, 1 by 4 and so on, the function is not defined. So therefore we can say that is f of x is discontinuous, f of x is discontinuous at x equal to 1 by 2, 1 by 3, 1 by 4 and so on. So, whenever you are considering such type of fractions, the function is not defining. So, therefore, we can say that the function is discontinuous at these points. So, here we have one property of Riemann integrable function, that is a bounded function f having a finite number of points of discontinuity on AB is integrable on AB. So, here a bounded function f. So, already here we know that f of x is bounded and it has finite number of points of discontinuity on the closed intervals AB, but here the closed interval is 0, 1. Hence, the function f is Riemann integrable on the same interval. So, therefore, here we can consider directly, that is f of x is discontinuous at these points. So, therefore, here we can write that a bounded function having a finite number of points of discontinuity is R integrable. So, therefore, we can say that f of x equal to minus 1 whole power r minus 1 is R integrable on the closed interval 0, 1. So, therefore, this is the first part of the proof. So, here we need to prove that, show that f of x is R integrable. So, that we have proved f of x is Riemann integrable on the closed interval 0, 1. And next we need to show that integration over 0 to 1 f of x dx is equal to log 4 minus 1. So, let us prove that one. Now, integration over 0 to 1 f of x dx is equal to limit as n tends to infinity UPF, limit as n tends to infinity UPF. So, that is the upper sum of the function f on the partition P. So, whenever n is tending to infinity means we are considering infinite number of sub intervals to get the appropriate area under the curve. So, therefore, it is equal to limit as n tends to infinity. So, let us substitute the formula of UPF, that is summation over r equal to 1 to n capital MR into delta r. Now, it is equal to limit as n tends to infinity. So, here it is m1 delta 1 plus m2 delta 2. It is the expansion of the formula summation over r is equal to 1 to n mr delta r plus m3 delta 3 and so on mn delta n. So, now it is equal to limit as n tends to infinity. So, here m1 is the supremum of the first subinterval, m2 is the supremum for the second subinterval and so on. And here delta 1, that is the length of the first subinterval, delta 2 length of the second subinterval and so on, delta n is the length of nth subinterval. So, now here m1. So, we know that the function f of x lies between 1 and minus 1, right. Means the minimum value of f of x is minus 1 and the maximum value of f of x is 1. So, therefore, whenever or independent of x, these two are the maximum and minimum values of x. So, therefore, here for the first subinterval The first subinterval is 1 by 2 to 1, next 1 by 3 to 1 by 2, 1 by 4 to 1 by 3, these are the subintervals. And here the value of the function, in the first interval f of x is equal to 1, in the second interval f of x equal to minus 1, and in the third interval it is plus 1, minus 1, plus 1, minus 1, alternatively it will come. And the subintervals, the first subinterval is 1 by 2, 1, 1 by 3 to 1 by 2, 1 by 4 to 1 by 3, 1 by 5 to 1 by 4, and so on, 1 by n plus 1 to 1 by n. So therefore here delta 1 is the length of the first subinterval, that is equal to what? Upper limit minus lower limit. Second, delta 2, upper limit minus lower limit. Similarly delta 3, that is 1 by 3 minus 1 by 4, and so on up to n. So therefore now let us substitute these values in that expansion of the formula. So here f of x, it is the m1, the maximum value of f of x, and m2, supremum of the function in the second subinterval. So it is the second subinterval, and here f of x equal to minus 1. So that is the constant function, hence supremum and infimum both will be equal to minus 1 only. So therefore here now substitute the values of them. m1 is plus 1 in the first subinterval, and delta 1 is 1 minus 1 by 2, upper limit minus lower limit. And similarly m2 is minus 1, and here it is 1 by 2 minus 1 by 3 plus m3 is again plus 1 into 1 by 3 minus 1 by 4, and so on. Here mn, the last interval, it is minus 1 whole power n minus 1, right, because depending on the value of n, because in the last interval f of x equal to what? Minus 1 whole power n minus 1, and here it is 1 by n minus 1 divided by n plus 1. Now here simplifying the terms, now 1 minus 1 by 2 as it is, next minus 1 into 1 by 2, that is minus 1 by 2, minus into minus plus 1 by 3, and here 1 into 1 by 3, that is 1 by 3, then minus 1 by 4, and so on up to infinity, because n is taking the values up to infinity. So therefore here we got infinite terms. Then it is equal to 1 minus, so minus 1 by 2 minus 1 by 2, that is minus 2 by 2, plus 1 by 3 1 by 3, that is 2 by 3, minus 1 by 4, and next term will also be 1 by 4, that is minus 2 by 4, and so on up to infinity. Then next, adding and subtracting 1. So therefore here it is integration over 0 to 1 f of x dx is equal to 1 plus 1, we are adding 1, and next we need to subtract. Then it is minus 2 by 2 plus 2 by 3 minus 2 by 4, and so on up to infinity, then minus 1. So here we have added 1 and we have subtracted 1. Now this becomes 2, 1 plus 1 2, then it is 2 by 2 plus 2 by 3 minus 2 by 4, and so on up to infinity, minus 1. Then we can take the 2 common in the numerators of the all the terms, then it is 2, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, and so on up to infinity, minus 1. Then here by using the expansion that log of 1 plus x, by using the expansion log of 1 plus x, that is equal to 1 minus x by 2 plus x square by 3 minus x cube by 4, and so on up to infinity. Log of 1 plus x, if x equal to 1, that is 1 by 2, 1 by 3, 1 by 4. If x equal to 2, that is 2 by 2, 2 square by 3, 2 cube by 4, and so on. So, here now compare this term, that is 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 and so on to infinity to this expansion. Here in place of 1 we have 1, and for the second term we have minus 1 by 2, here it is x by 2, right. Then the third term is x square by 3, now it is 1 by 3. This one can be written as 1 square also, that 1 square is equal to 1 itself. So, 1 square by 3 minus 1 cube by 4, 1 cube equal to 1 only. So, therefore, we can write this as log of 1 plus 1, because here x equal to 1 minus 1. So, it is equal to 2 log 2 minus 1, that is log 2 square minus 1, by using the properties of logarithm, that is m log n is equal to log n power m. So, that is log 2 square minus 1. So, therefore, it implies that log 4 minus 1. So, therefore, it is the required proof. Here we have proved that f of x is Riemann integrable, and also the value of that Riemann integral is equal to log 4 minus 1, that is integration over 0 to 1 f of x dx is equal to log 4 minus 1.